So our first step is to take these two representations of Hamilton's equations and use them to show F equals ma. So let's try this out here. So now we're going to do the proofs. So proof, we're going to do step 1. So we want to compute mass times acceleration, and what we're hoping to get, we're not sure yet, but we're hoping what we're going to get then is our force back again. Right? So now, the way we would prove this is we would work directly from the definition of acceleration. Now, by acceleration, of course, we mean the second derivative of the time derivative of the position of our particle. But now, once again, we're talking about a quantum system, so we never know exactly where our particle is as it moves around and accelerates. We can, though, particularly if the packet's very narrow, where things will look like their typical classical behavior, when they're very narrow, we can replace the position of the effective particle, right, the position of our packet, with the average of the position operator. So we would then say we're going to look at the acceleration then of the average position of our packet. Now, of course, this is two time derivatives, and we know how to take two time derivatives. You do that by taking the first derivative of the first derivative. So my job is to take the first derivative of x with respect to time t, and then I can take the second derivative. Now, the first derivative of x with respect to time t, by supposition, right? We are supposing these two statements right now. We will come back and prove them later, but by supposition, the time derivative of the position should just be the average position, should be the average momentum divided by the mass. So this will be the average of p divided by the mass of my particle. Now, of course, one very nice thing happens. You can see that the masses cancel out. So I'm actually left just with then the time derivative of the average of the momentum of my packet. Now, average of the time derivative of the momentum, that's the second piece that we will be assuming for now. That just gives me equal to the average of the derivative of the potential with respect to x. And of course, the average of that derivative is just the same thing as the average of the force experienced by particles at the location of the center of my packet. So then that will actually establish for us F equals ma. So step 1 was pretty easy. The key thing is we need to prove these two key pieces, the time derivative of the x, average of x, and the time derivative of the average of p. That then takes us to the second step.